x prime of t, yeah, this with respect to t, what do I get? Well, this is the sum over I, and then the only function of t is hiding in this exponent, so in the end I get ci lambda I e to lambda I t xi. Yeah? That's just high school calculus, not anything fancy. And what is this product, lambda I times xi? Well, xi by construction is just an eigenvector of A, right? So this is the same thing as the sum over I of ci e to the lambda I t times A x I. Yeah? And finally, I can factor the A, and I get that this is A times the sum over I, ci e to the lambda I t x I, right? Well, this thing, if you look back, is our original formula for x of t. So in the end, I got A x of t. In other words, right, x prime equals ax. So I solve our equation in closed form. So if I ever write down an ODE in this form, x prime equals ax, I have two options. Either I can do fancy time stepping, right? What is that, rung, kata, and all of these tools that we use, RK3, which I always confuse with that football player on the Redskins. Or I can simply find the eigenvectors of this matrix A, and I can just write down a solution to this ODE for all time. By the way, I started with springs, and springs have this oscillatory behavior, right? Springs like to wobble. But it kind of doesn't really look like that should be the case, because I got e to the lambda I t here, and the exponents tend to look like growing or shrinking functions, right? Depending on the sign of lambda. So what does this suggest about the eigenvalues of this matrix A? They're complex. Yeah, right? Because remember our favorite theorem, right? This thing that high school math kids really like to quote, that e to the I theta is equal to cosine of theta plus I sine of theta. Right? So this is how to get oscillatory stuff out of exponential stuff. So this suggests that there's something kind of complicated going on with this matrix A. But anyway, we're going to hide that under the rug for now. Yeah. One more aside. Let's say I wanted to solve Ax equals b. And I write x as a combination of the eigenvectors of A. Is this something I probably want to do in practice, by the way? No. Right? Because we're going to find that computing eigenvectors is strictly harder than inverting matrices. Right? So we're probably not going to want to do this, but let's say that we did, just for fun. Can anybody guess what x would have to be? You can use a similar trick. Well, you sort of know. Like, let's say that I applied A to B here, right? I've computed the product AB. What would happen? Well, I get C1 times lambda 1 x1 plus C1 times lambda 2 times x2, and so on. Right? So in fact, if I made this choice, x equals C1 over lambda 1, and all the way to lambda n, assuming these lambdas are non-zero, right? Which is the same thing as assuming your matrix is invertible, by the way. Then what happens when I multiply this by A? Well, when I multiply x1 by A, I get a lambda 1 x1, and that cancels this lambda 1 out, and I just recover B again. Right? So I can solve Ax equals B pretty easily just using the eigenvectors of A. When this will be useful is if it turns out that A is pretty poorly conditioned and you have some really big eigenvectors and some really small ones. Right? What happens to big lambdas here? Well, you're dividing by them, so they're pretty much zeroing out that component. Right? So one trick that you can use is to just compute the first few small eigenvectors of A and get a pretty good approximate for x. Yeah, I'm just ignoring the sort of small terms. Cool. Now, for yet another completely different application of eigenvectors. Do you see what I'm trying to do here? I want to convince you that eigenvectors are like the bee's knees, that these are things that we want in machine learning, in graphics, in vision, and whatever else is in the title of this course. And so it's, I tried to choose one example from each to kind of get you started, and there are so many more. Go to my office hours and I can just expound upon eigen things forever, right? For me, I use eigenvectors to solve very fancy PDEs on surfaces and do mapping and all kinds of cool stuff. Anyway, so in this case, we're going to talk about a technique called spectral embedding. By the way, whenever you hear the word spectrum, it's probably talking about eigenvectors. In this class, if it's in 248, it might be talking about like color perception or something. But for us, spectrum means eigen things. Okay? And so spectral embedding probably suggests that we're going to use eigenvector techniques to embed things. Okay, this is almost a little bit of a similar application to the first one we talked about today. We wanted this nice variance maximizing projection. Right. So, let's say, that's a good setup. Let's say that I have a big database of photographs, right? Let's see, this is like the setup for a bunch of different punchlines in 205A. But let's say that I go on a tour and I take a bunch of photos. For once, my photos were okay. I don't need to worry about deconvolution and all the stuff we talked about before. Yeah? But I have this problem that I'm kind of an excited tourist and I take a ton of photos, just every which way. I'm just taking photos, right? And I've got so many, I want like a nice way, and nothing else to just order them so that like similar photos I can just scoop past really quick and not have to worry about, skipping something interesting. Right? It's kind of a reasonable thing. So I want to put them on just one timeline, all my photographs, so that sort of nearby things in the timeline are sort of are similar photos, and far away things in the timeline are very different photos. Right? So maybe in addition, so in this case we have n different photographs in my data set. In addition, I write down some wij number, and w is going to say how similar photo I and photo j are. Right? So for example, in the simplest possible thing, maybe I just bin all of the different colors in my photograph, right? So like a photo taken during the day will have a histogram of colors that looks like that. A photo taken at night will have a histogram of colors that look like that, right? Where this is dark to light. Right? And I just measure a bunch of distance between all of these different things, and then I take e to the minus that. Okay? So this is some measure of how similar two photos are. In fact, there's a whole literature on how to compute these W's, but that's outside of the scope of our class. And I think it's fair to assume that W is symmetric, namely Wij equals Wji. Right? This is just a similar number, and that's positive. Okay. And again, what I'm going to do is I want n numbers just on the real line that sort of order these photos in a way that respects this similarity metric. So things that are nearby on the real line correspond to similar photos, and things that are far away correspond to different photos. Now, is it enough to just kind of look at this matrix W and like take a row and just sort the values in that row? No. Because I don't know that these W's satisfy the triangle inequality. I don't know that they sit on a line. That's just some heuristic that I've written down that measures how similar photos are. But I want to project onto a line in a way that makes sense. Okay. So how can we do this? Well, what do you think I'm going to do? Come on, pattern recognition in CS205. What's the next step Justin's going to do? I'm going to write down an energy. Yeah? That's what we do here. So in particular, let's say that I have a bunch of these different xi's. Okay. And xi minus xj is just how far apart they are on this embedding on the real line. Right? And what I'm going to say is, okay, so this number squared is how far apart they are, and what I care about is wij times this distance squared. So what is this saying? That when wij is big, I want this distance to be small. Yeah? In particular, when wij is big, this is saying that photo I is similar to photo j, and thus I want the difference between xi and xj to be pretty small. Yeah? Whereas if wij is 0, like photo I and photo j are just completely different, then I don't really care if they're close to each other or not. Right? So this is just a weighted sum of a bunch of squares of differences. Everybody nods, we agree this is a reasonable model. In fact, this is used in practice law. Yes, Kathy?
So you're saying x minus xj? So that means that those two, like, it's really small and they're really similar?
Yeah.
Okay.
So, like, remember our goal is I want to, like, make a timeline of my vacation, right? So I'm going to put along the line, like, a bunch of photos that I've taken. And somehow I want that guys that are nearby on this timeline have big wij because they're similar, right? So I want to couple together similar things. Okay. So how are we going to solve this problem? We're going to minimize e. What's the minimum of e?
The weighted average.
Nope. What's the minimum of e? 0. Yeah. In particular, I can take all of my x's to equal 0. This is the minimum of e, because they're all close to each other. And since W is positive, we want everything to be close. And you can't get closer than 0. So that's a boring answer. We need to fix that. So again, we want to minimize E, but we decided that minimizing E just in a vacuum isn't enough. So what do we do? Well, okay. So let's think, right, we have this sort of decision tree of CS205, what we're going to do. We worked on a quadratic energy, right? And if we could minimize it and get something non-boring, we might stop there and do something like Gaussian elimination, right? But in fact, we can't do that because the answer is boring, so we need to regularize. So what do you think we're going to do? We're going to add a constraint, the norm of x equal 1, right? This means that everything can't be 0 because you've got to have non-zero elements in this vector. Is this enough? No. Why isn't it enough?
So you can shift the narrow to some positive values, and so that the norm of the axis is still 1.
Exactly. So let's do this. Let's write this out. In particular, remember we're going to have n photographs. So let's say that I put my x vector is going to equal this: 1 over the square root of n, 1 over the square root of n, dot dot dot, 1 over the square root of n. What is the norm of this vector? Well, so what are we going to do? We're going to sum up all of these things squared. Okay? Each of these squared is just 1 over n. There are n of them. So the norm of this thing is 1. Well, shoot, we've foiled again. So, okay, so we can think of this constraint as making sure that something in our vector is not 0, but we'd still like to have an additional constraint, which says that this is non-boring. Yeah? So the simplest possible one I could say is that my vector sums to 0. By the way, do you understand the notation in this slide? So this vector is just the vector that says 1, 1, 1, 1, 1, 1, 1, 1, 1. Yeah? So I'm saying the sum of x is equal to 0, all that xi's. Right? And this cancels out this case because we know that some of the xi's are going to have to be negative and some of them are going to have to be positive. Yeah? And now this gives us a non-trivial embedding. You can try this at home, by the way. Just play with it. It's fun. Easy to do in MATLAB. Alright, so this is the problem we'd like to solve. And of course, this doesn't really look like our last 3 examples of eigenvector problems, or the ones from your homework, right? This additional kind of funky constraint. So my claim is that nothing too weird happens. Let's do our homework here. Okay. Oh, oops. So, right. So, continuing in our pattern recognition for CS205A, we know Justin has written out an energy, he's written out enough constraints that he knows his energy is not boring. Now what is he going to do? Leonard, what am I going to do?
Take the gradient of the energy.
Yes, I'm going to write the Lagrange multiplier function down and take his gradient. This is the only thing I know how to do. Yeah? This is the same pattern that's in the last couple lectures and the same one for the next, 17. So, right. So what is the Lagrange multiplier function now? Well, it's e of x, which we decided was the sum over ij of wij xi minus xj squared, right? But we have constraints. Now we have 2 constraints. I'm going to have minus lambda times x, we'll think of this as a vector, transpose x minus 1, minus mu times 1 dot x. Right? Just another Lagrange multiplier function. So what's going to happen when we find critical points of this guy? Let's take his gradient with respect to x now of this Lagrange multiplier function. Yeah? Actually, let's not. I want to simplify a little bit first. Sorry. Yeah, my bad. In particular, let's expand this square. Yeah. So what are we going to do? We're going to sum over ij, delta ij, and this is xi squared minus 2xi xj, that's an I, plus xj squared minus lambda x transpose x minus 1 minus mu 1 dot. Yeah? I haven't anything too exciting yet. In fact, probably I could have stopped carrying around these things, but that's okay. Now, we can split this into 3 sums. Yeah? So I claim that this is equal to the sum over, the sum over I of, we'll say aixi squared minus 2 sum over ij of w ij xi xj plus the sum over j of bj xj squared minus, and then we'll just say the usual logarithm of parsing. Okay? And what are xi, or ai and bj here? Well, look what happened. So if I only look at this term, right, this is summed over I and j, but the xi, which is our variable, this is our unknown, only cares about I. So we can say that ai is the sum over j of wij. Yeah? Ugh. Not going to get to the end of this lecture. That's okay. Yeah? And bj, what do you think bj is going to be? It's going to be the sum over I of wij. Right? By the way, w is symmetric, yeah? So, ai equals bj. It's all the same. So in the end, what did we get? We got that lambda, well, you can think of it as x transpose, and then we'll say, we'll think of this a diagonal matrix capital A, whose diagonal vectors are the AIs. So it's going to look like 2 capital A minus 2 double capital W. Yeah. And the x transpose x minus 1 minus mu. Everybody see what I did there? Right? Because this thing looks like the sum over I and j with the W on the inside. By the way, your homework problem 3 is going to use a very similar trick. Yeah? Okay. Cool. Well, this looks like a thing that we can differentiate set equal to 0 and solve. Yeah? So, in particular, oh, by the way, so I think I can go to the next slide now. We know, know that our energy, right? Our energy is just the first part of this. Looks like this guy. Thankfully, I haven't made a mistake yet. It's only a matter of time. And now we want to find this surprising result, which is I want the second smallest eigenvector of 2a minus 2w. By the way, this matrix is clearly symmetric, right? Because this is diagonal and w is symmetric by definition. And it's also positive definite because it's equal to this positive number over here. Yeah? But we're not going to worry about that today. Right. So, in the end, we got to find the derivative of this guy once again. So his gradient of lambda with respect to x is going to be what? Well, it'll be, I get a factor of 2 up. Yeah, whatever. Okay, so I guess in the way that I've set this up here, we'll call this matrix, we'll call him M, right? He's symmetric. So you're going to get 4mx, right? You get a factor of 2 every time you do a derivative like this on a symmetric matrix. By the way, this I think is a typo on my notes. Sorry. If you haven't noticed yet, I make a lot of it. 2 lambda x. But now we have this additional kind of annoying thing, which is mu times a vector of 1s. This equals 0. Right? So in particular, we get, so let's redefine lambda and get rid of some of these constants. Right? Since lambda is just some number anyway, let's say that in fact we're going to want to solve mx equals lambda bar x plus mu bar times this vector of 1s. You can always do that. So, what is mu bar? It's not entirely clear, right? Okay, so let's think about what is this matrix M? What is M times the vector of 1s? Well, this is just the sum of the rows of M. What is the sum of the rows of A? The sum of rows of A are just the diagonal elements of A, because A is a diagonal matrix. Yeah? What are the sums of the rows of W? Well, they're exactly the A's by definition, right? A is the sum of each row I of W, right? So in particular, what this tells us is that M times a vector of 1s is equal to 0. Ain't that cute? So what happens now if I pre-multiply this thing is, it looks like this. So I can say 0 is equal to 1 transpose mx, right, by what I just showed. Since m is symmetric, I can put 1 on the left and I haven't screwed anything up. And what is this equal to? Lambda 1 transpose x, lambda bar, I suppose, plus mu bar times n. Right? 1 dot itself is just the number of dimensions. Okay. What is 1 dot x? What was our optimization? Let's go back. Well, we have 1 dot x. It's 0. Yeah? This thing is 0. And this whole darn thing is equal to 0. In fact, this isn't a vector, this is a scalar. Sorry. So what does this tell us about mu? It's 0. Yeah, mu bar is 0. So what did I just prove to you? I proved to you that in fact we want to solve mx equals lambda bar x for some x plus 0. Yeah. Yes. Scott.
Can you explain again where that 1 dot x came from?
Where? Well, it was just part of our optimization. Remember what happened is if we didn't have it, we could get a constant solution that was just 1 over the square root of n a bunch of times over. But by asking that x sums to 0, then you get positive and negative things in x because they got to cancel out. Cool? So, what am I searching for? I'm searching for something that is an eigenvector of m. It sums to 0 and it isn't a constant function. It's easy to check that 1, in fact I already did check for you, that 1 is an eigenvector of m with eigenvalue 0. And since m is symmetric, all the other ones are orthogonal to 1, which means that they're all going to sum to 0. So all of the eigenvectors of m, except for this first one, sum to 0. We'll come back to that in a few minutes. And, just like before, our energy is going to be equal to the eigenvalue. So what do we want? We want to minimize this function. So we want the second smallest eigenvector, we want the eigenvector corresponding to the second smallest eigenvalue of this matrix M, and that's going to solve our problem. So even when we added the second constraint that it's orthogonal to this vector 1, we still recovered an eigenvector problem. Can I see a pattern here? So let's step back a little bit and kind of summarize what we know so far. So first of all, we know the definition of an eigenvector. I think that's clear. It's easy to extend to the complex numbers, by the way, because you just call them complex numbers, and then now you have a complex eigenvalue. By the way, and I think probably the one thing Math 51 does a very good job of hammering into your brains is that the scale of x doesn't matter, right? 2 times x is still an eigenvector with the same eigenvalue. We're going to call the spectrum of A the set of eigenvalues of the matrix A. Right? And the spectral radius, this row of A, is the largest eigenvalue that maximizes it, the eigenvalue with the norm, the largest norm. That I managed to stutter my way through that. It's the biggest eigenvalue. If you look at the first extra credit question on your homework this time, you'll see that there's a surprising connection between matrix norms and eigenvalues of your matrix, which is not obvious to me, by the way. And it's a pretty recent theorem. It's within the last couple decades. Okay. And when do eigenproblems come out in the wild? Well, we've seen an example of all 3 of these now. Right? Certainly when you solve differential equation problems, remember, like this thing with the springs, partial differential equations as well. We'll come back to that later. When you have this thing that looks like minimize or maximize the norm of a times x such that the norm of x equals 1. Right? This was sort of the pattern that we saw a lot today. In fact, by the way, you can generalize this a little bit to the norm of bx equals 1. That's called a generalized eigenvalue. Right? That's going to end up looking like what? Ax equals lambda bx, or A transpose A. And then finally, you can have something called the Rayleigh quotient. And when you want to find critical points of this ratio here, those are exactly the eigenvalues. These are all problems that you can, this is sort of the type of problem that you might see in the wild that you should just look at and immediately say, eigenvalues, done. Right? And then not write your own code, because writing code for eigenvalues is a big pain. We'll learn that next time. Okay. There are lots of different properties of eigenvalues and eigenvectors. We'll cover a couple today, and we'll finish off on Monday, I guess. We aren't going to prove these two. If you're a stickler, I did write nice, rigorous proofs, of course notes. By the way, for fun, I was reading that paper about like not liking determinants, and I kind of bought into that last summer, and so all the proofs don't have determinants, which might be not what you're not used to seeing. Anyway, right. So first of all, every matrix has at least one eigenvector. Right? One calculus way to prove that is to say, well, this Rayleigh quotient function is some function, and it has at least one critical point, and that critical point is an eigenvector. That's not the proof that I give you in course notes, but it is a proof. Also, if you have two different eigenvalues, your eigenvectors must be linearly independent. Right? These are probably facts you've seen before, but you should double check. And you can check the course notes. We don't have time in lecture. These are facts you should know. Now, what do these two facts together tell you about life? Well, the first one tells you you've got at least one eigenvalue, and the second one tells you you've got at least n, at most n, rather, right? Because if you have n different eigenvalues, what happens? Well, then you have n different eigenvectors, they span Rn, and you're done, right? Because otherwise it's got to be linearly dependent. Yeah? So this is nice. We now have a search problem, we know what we're looking for, and we know there's a finite number of things we're going to find. This is good. Now the way that you learn in Math 51 to compute eigenvectors is using the characteristic equation, right? And that is a horrible way to compute eigenvectors, because it requires taking determinants, and if you think about the way you take a determinant, write down a 10 by 10 matrix and try to take its determinant. Just try, I dare you. I think you'll get very bored very quickly. I was talking to a friend that's very into this Zen stuff, and they're talking about like a good exercise is to just buy a bucket of rice and just start counting grains of rice. And you'll be surprised with how quickly this becomes frustrating. Computing the determinant of a big matrix is the simple way. And in fact, that's provable. It's like provably frustrating, right? If you take one of these upper level, like 361, I think you'll prove that. Okay, anyway. The matrix is non-defective if it has a complete set of eigenvectors, namely that it's an n by n matrix and it has n eigenvectors and they're linearly independent and they span Rn. Right? We're going to learn soon that this is not an uncommon case, but we'll call it non-defective because when it's defective, lots of scary things can happen to your matrix. In particular, what does this mean? Why do we call it a diagonalizable matrix? Is maybe a word you've seen before but haven't really thought about. Well, remember that an eigenvalue satisfies ax equals lambda x, yeah? So let's say that I do my usual trick, and I'm going to write a matrix X, which is just the first eigenvector, the second eigenvector, all the way to the nth eigenvector, right? And now, what is AX? Well, it's the same as applying A to each of these columns, right? So in the end, you're going to get a matrix that looks like lambda 1 times x1, which is lambda n times xn. Right? Well, this looks like a column operation. See what I did here? These are scaling the columns of x by different lambdas. So in particular, this is x times this matrix, lambda 1, lambda 2, lambda n, 0. Yeah? Right? It's a column operation. Scaling. We're good at that from our last lecture. Yeah? So this thing is equal to x times capital lambda. Or I guess I called it d. Sorry. In this class. So what we proved, we showed that ax is equal to xd, and since the columns of x span Rn, in this case that means that x is invertible, so I can say d is equal to x inverse ax. So what did I do? I just diagonalized a. Right? D is diagonal, a is not. Yeah? Okay. So somehow non-defective matrices are really nice and have a lot of properties that we like, and we're going to take advantage of that soon. So for a minute, we're going to talk about complex matrices, and then we're probably going to concern ourselves mostly with real numbers in this class, but I can't, in good faith, talk about eigenvectors without mentioning complex stuff for a little bit. First of all, complex number, right? That's one that has an imaginary part. Hopefully we've all seen that in some form or another. Right? Then we write down the complex conjugate of a number z. We'll write z as a plus bi. Complex conjugate, assuming a and b are real, is a minus bi. How many of us have seen this before? Yeah? Like high school, totally bored, sweet. Okay. What you might not have seen is that we're going to define a generalization of the transpose of a matrix. We're going to say the thing that we think of as the transpose of a complex matrix, right? Notice that I used to say Rm by n, but here this is Cm by n. It's going to be the conjugate transpose. We're going to call that A to the H. And that's going to be A conjugate, so we're just going to conjugate every element of A, and then transpose that matrix. And it turns out that most theorems that we prove about matrix transposes carry to complex matrices by considering this weird object here. There's a reason for that. And a Hermitian matrix is the generalization of a symmetric matrix, and it is a matrix that is equal to his complex conjugate transpose. Right? So A equals AH. By the way, the H stands for Hermitian. Or what is this guy's name? Hermit? I don't know. Sorry. Yeah, so A is equal to AH. If I were a better mathematician, I'd remember this guy's name. I don't know. You guys aren't helping me. Okay. There are lots of properties of Hermitian matrices, and unfortunately we've got 8 minutes, but we'll see what we can do here. So first, probably most importantly, all eigenvalues of Hermitian matrices are real. So Hermitian matrices may be complex. They might have imaginary numbers in them, but in the end, their eigenvalues have got to be real. How can we prove that? Well, it's actually kind of a finicky little proof. So normally we think about dot products, but just like everything else has to be slightly different in complex number land, the dot product of two complex vectors has to be slightly different. So we're going to say that the inner product, by the way, this notation also appears on your homework, yes? This thing is going to be like the dot product for x and y are complex vectors. Right? It's going to be like the dot product. It's going to be equal to, let's make sure I get this right, x transpose, and normally we just have y here, right? But instead we're going to say y bar. Right? So you're going to take the second guy, flip all of his complex parts, and then take the dot product. This is the appropriate inner product on the space of complexness. Why is that? Well, for one thing, what is the norm, or the length of a plus bi? Well, it should be a squared plus b squared, right? Square root of that. Right? And how can you get that? Well, that's the same as a plus bi times a minus bi. Okay. So notice that I've just kind of encoded that by taking the conjugate. Okay. So let's see if we can prove this claim in like 4 minutes or less. So let's say that ax is equal to lambda x. And so far we don't know if lambda is complex, real, imaginary, whatever. So what do we know? Well, we do know that x has norm 1 because it's an eigenvector. We can always do that. Yeah? So in particular, lambda is equal to lambda times the inner product of x in itself. Oops. Because that number is just 1. Yeah? 1 doesn't do anything to the product. Okay. And because it's a dot product, it's pretty easy to see that that's the same as putting lambda in the inside of this thing. By the way, this is looking very similar to your third homework problem, yeah? That's so similar. Okay. And lambda x, what is lambda x equal to? We don't know much about lambda, but we know one thing. It's an